This video made possible by Incogni. How do you make your tool hard? No, not like that, straight to horny jail with all of you. I mean, when you want a workshop tool, you don't want a floppy noodle. You need it to stay firm and in its proper shape. No one wants a chisel that's useless after only a few blows. You need something that can take a pounding for hours. And generally, knives and other cutting tools work best when they're sharp. So you want them to be made of a hard material that won't bend or chip. No butcher wants a dull tool when they're handling their meat. But manufacturing a tool in the first place often requires the starting material to be in a softer, malleable state. So you need to be able to make it go soft or hard at different points in the manufacturing process. Humanity's answer to this is the wonder material we call steel. At its simplest, steel is a mixture of iron with a very small amount of carbon. But modern steel often has a variety of other elements mixed in for added flavor and to tweak its properties. Today we're going to be taking a trip through time and learn first how we convert iron into steel, and then how we can make steel hard. From the oldest known methods using clay and charcoal, to the most modern that use molten baths of boiling salt, or vacuum systems and plasma. And by the end, we'll have converted dirt-cheap iron into a hard steel knife, and show you how you can even harden stainless steel, which is normally impossible. But before we get to steel, let's take one step back and look at pure iron. Iron as a pure metal is honestly kind of mediocre. It can't hold an edge, and it's quite soft and bendy. And worse than that, it's actually pretty difficult to make. The issue is that its melting point is really high, well over 1500 degrees Celsius. So to take iron ore and convert it to iron requires a system that can get at least up to its melting point, though the hotter the better. Originally, this meant building a bloomery, which is basically just a big tube made out of clay or mud, with a pipe at the bottom you can blow air through called a tuyere. Now, wood doesn't burn hot enough to make iron, which is one of the many reasons that it took so long for humans to master. Before you can even start up the bloomery, you get to spend days and days cooking wood into charcoal, which burns much hotter. Then you fill up the bloomery with your charcoal, and once everything is burning and hot, you start feeding in iron ore and more charcoal in the top. There are many videos of making iron this way, and it's simple enough that even nearly naked in the jungle, you can make it work. The end result is a spongy mass of iron and slag that then has to be worked to collect all the little molten bits of iron and make them stick together into a cohesive chunk. That chunk then has to be worked, folded, and welded some more to get all of the junk out of it, and the result is what was called wrought iron. However, wrought iron is literally just iron, it's not steel. Steel originally was just a lucky bonus item that came as part of this process. Some of that spongy initial mass of metal will have dissolved the perfect amount of carbon into it and become a hardenable steel. So the blacksmiths would have to isolate those bits to be used for making tools, while the rest was converted to wrought. Obviously, this is not efficient, and the yield of steel is terrible. So you need a way to convert the bulk wrought iron into proper steel so it can be used for tools too. By far, the easiest way to do this is with a process called case hardening. Essentially, the idea is to treat a piece of iron such that the outer surface is converted to a hardenable steel skin. So you preform your tool, be it a file or a chisel or whatever else, then you case harden it to make the working edge hard. This leaves the core still relatively soft and ductile so the piece won't snap, but the cutting edge will now stay sharp. This is also the oldest way to make steel on purpose. We're not really sure who first figured it out, but people most likely noticed that pieces of iron left hot and buried in coals for a while got strangely hard when dunked in water, in a way that normal iron didn't. Eventually, this process was refined, such that you bury a piece of iron in charcoal in a flame-proof container, and then bring it up to a red heat and bake for a while. This will cause the charcoal to release things like carbon monoxide, which can then diffuse slowly into the iron and raise the carbon content. This, as you might imagine, is not a fast process. Since the iron is still solid, the diffusion rate is very slow, between 0.1 and 0.2 millimeters of depth per hour. But since we only need a relatively thin, hard skin, that's actually fine. Originally, they would have used clay to make a vessel for this, but pretty much any flame-proof box works. Though we don't want it to be totally sealed. Gases do need to be able to escape, so even a clay box would have a small hole in it. Or you can weld up a box to fit your items. We made lots of these test samples out of some 1/4-inch square bar made out of mild steel, which is the closest modern equivalent to pure iron. It can't harden, and it's the sort of cheap iron that you would find at a hardware store. Good enough for rebar or a fence, but not something that you're going to make a cutting tool out of. We're going to do 3 runs to show you the difference between a control piece and 15, 30, and 60 minutes cooking at 950 degrees. Now, a wood fire would actually be perfectly fine for this, but my landlord probably wouldn't appreciate me setting up a bonfire in the lab, so we're going to use our much more accurate kiln for this. When it comes out, it's still ripping hot, but to keep the timing consistent, we opened the still hot box to fish out the bars. This usually meant that the charcoal was red hot and would burn a little bit, and the bars were red as well. We allowed these to slowly cool so they don't harden yet. Because remember, just because there's some carbon in here now doesn't mean they're hard yet. And the way you can tell is similar to how you pick good bread, from the sound.
How do you tell how good bread is without tasting it? Not the smell, not the look, but the sound, the crust. Listen. Oh, a symphony of crackle. Only great bread sound this way.
To demonstrate this, I've got 2 test pieces. This first one is our control and it's dead soft. If I take a file to it, it makes a low-pitched sound from the metal being cut. And you can see that the file very easily leaves a mark on the metal as it's starting to reshape it. Now, let's compare that to a hardened piece. Whoops, sorry, that must be the wrong end. Let me flip this around and try that again. Okay, now you should have heard the difference. It's a much higher pitched noise, and the file is hardly able to scratch it. What you're hearing is the file skating and bouncing over the metal rather than cutting it. So, now the question remains, how do we go from soft to hard? Well, that can be a very personal question, but no matter the case, we're going to need some lube, or rather, coolant. If you've watched blacksmithing content before, this is the most exciting part of the process. The piece of steel has to be heated above 800 degrees to a nice orange color. Then, while it's still hot, it's plunged into coolant, which is often oil, meaning a big burst of flame as the sudden flush of oil vapor burns. We'll do a comparison of different quenching fluids in a minute, but for the sake of our case hardening test, we're just going to use canola oil. Most oils can work, but canola is cheap and it doesn't release as many toxic fumes. While we get the forge up to temp, have a quick look at the 4 test pieces fresh from case hardening. You can see a distinct color difference as the layer of carbides and oxides on the surface grew thicker, with increasing cook time. Anyway, once the forge was hot, we popped in the test pieces, being very careful to keep track of which one was which. Then, when they're good and hot, each was quenched in oil. So, how'd they turn out? This time, rather than just any old file, we picked up a set of hardness testing files. These are each calibrated to a specific hardness, so if the file can cut the metal, it must be less hard than the file, and vice versa. Our control piece, as we expected, fared poorly. Even though it's been heated and quenched, it's still just iron, so it didn't harden at all. Even the lowest file cut it with ease. But the case-hardened pieces are very different. Even after 15 minutes, there's now a very hard skin on the outside, and it takes a 55 Rockwell file to cut it. As we go up in time, this only gets better, and by the 60-minute sample, only the highest 65 Rockwell file got any purchase, and even then only barely. So, as you can see, this is a really fast and effective way to turn crap iron into a usable tool. The other test to see if we've made steel is to touch these to a grindstone. When it's pure iron, here we're using a piece of 99.99% electrolytic grade iron, we get long thin sparks of the pieces of iron burning mid-air. But as the carbon percentage increases, the sparks change. Mild steel, which has around 0.2% carbon or less, sparks with a bit more pizzazz, and you can see little explodey tufts at the end of the sparks. But now our case-hardened pieces look totally different. Really aggressive, explodey sparks, and lots more of them. This is the classic look of high carbon steel. Though, while this is a great trick, it comes with problems. What happens if you want to resharpen the tool? Most often, this means grinding with a stone to reshape and recreate the cutting edge. But remember, the hard layer is whisper thin, so as soon as you do that, you could be down to soft metal. That's why this technique works best for either very thin pieces, where you can get the carbon down into the core, or tools like files, which don't tend to get resharpened. If you're in the habit of buying old files or rasps and that sort of thing to forge into new items, sometimes you run into this problem, where what you thought was a nice piece of tool steel is actually just case-hardened iron. So when you reshape it, suddenly it won't hold an edge anymore. So how do we improve on this? Well, the first solution that people figured out was just cook it longer, also known as cementation. They would roast tons of wrought iron in a special cementation furnace, which is basically just a scaled-up version of our steel box and charcoal. And instead of cooking for an hour, they would cook for a week or more, so that carbon had time to diffuse all the way into the core. But this creates a new problem. You see, steel is actually only a very narrow range of carbon dissolved into iron. If you go too high, instead of both being hard and strong, it becomes hard and incredibly brittle, and will literally shatter apart on use. The ideal range is between 0.6 and 1.5% carbon, but this will vary a lot based on what other elements are mixed in. Above 4% and you get cast iron, which is much easier to melt and, well, cast, but it's also incredibly brittle and useless for tool making. So the cemented pieces had to be layered and welded to more wrought iron. This way, it evens out the carbon percentage to a more reasonable value throughout the whole piece. But at the same time, they were making pattern welded steel, which these days is often called Damascus. While we were doing our case hardening tests, we actually had some secret test pieces cooking that you hadn't seen yet. These are our cementation tests, and the idea was to cook these for as long as we could. Cumulatively, I think we got about 8 or 10 hours of cook time, though as you'll see later, we definitely needed to go longer. We only stopped because the box was developing a frighteningly large hole that was starting to let way too much air in. But anyway, just like before, you can see a distinct color difference between these and the raw pre-cooked metal. If we had cooked this longer, the surface would have become cracked and blistered, hence why this stuff was originally called blistered steel. Before we can use this, we need to clean up the surface and remove all of these oxides, so a quick pass on the belt sander was in order. As pattern welded steel goes, this is going to be pretty basic, but we're going to stack up 5 pieces. 3 of our cemented ones, with 2 regular pieces of mild steel. These could then be welded together, and I stuck a scrap bit of bar stock on for a handle. Now for the part where I get my exercise. Unlike many of the other channels that show off blacksmithing, I lack all of the big power tools, like a power hammer. So making these bits of steel stick together is just going to be a solid day or 2 of me pounding away with my right arm. I started by just initially heating the billet lightly so that when I sprinkle some borax on it, the borax will melt and stick. Borax is one of many fluxes that can be used to form a temporary airtight seal on the edges of a billet so that the metal's face stays clean. Then this needs to get basically as hot as my forge can manage. When it's hot enough that it almost hurts to look at, I can take a few gentle swings to start. I just want to set the weld a little bit before more flux and back in the fire. It's best to do forge welding when things are at their hottest for the best chance at it sticking. After a few rounds of pounding, heating, and more pounding, I was happy enough that the weld had stuck that I could start working on the sides and slowly forming this into a solid block. Since this is my first time doing this, I wanted to make sure the weld was good, so I let the billet cool off and ground through one side. And sure enough, it was a nice clean join for the most part. While it was cold, I figured it would be nice to do a quick test etch so you can see the layers. A little bit of ferric chloride was all it took, and sure enough, we see distinct layers. The darker parts are where the carbon dissolved in the most, and you can see that even with all that cook time, the carbon didn't penetrate all the way in, which is going to bite us later. While you forge the metal, the carbon will naturally diffuse throughout the billet, so as long as there's enough to keep the total block above a hardenable amount, you're good. But we have some other tricks we'll get to in a moment if we need more hardness. Anyway, this could be chucked back in the fire, and now that we know it's good, I'm going to start working it into the shape of a knife. I have always wanted to make my own chef knife, and I've watched enough hours of Alex Steele, Black Bear Forge, and many others that it almost felt like muscle memory to work through the steps of stretching and shaping the metal. Though I am no professional, so I'll leave explaining those steps to them. This was a ton of work to do entirely by hand and without a second person as the striker, but there is something immensely cathartic about being able to smash a piece of metal until it goes from a block to something beautiful. Of all of the machining and making stuff I've done over the years, there really is nothing quite like the rhythm of fire and forging. After the knife was shaped as best as I could with a hammer, it was on to grinding, and barely a few minutes into that process, my belt sander decided to commit ritual seppuku, so I had to pause and rebuild my entire grinding station and purchase a new belt sander. Which reminds me, if you're enjoying the video, consider becoming a patron of the channel. Links in the description. When the grinding was 95% on the way done, we're back to hardening. So the piece has to once again be brought up to an orange heat. It's also good to check the steel with a magnet at this point. When it's over the Curie temperature, the piece will stop being magnetic, and at that point it's hot enough to quench. This time, rather than canola, we went with water. This was for two reasons. First, I didn't have a big enough container, and importantly, I didn't have enough oil. Mildly awkward. But water also works, so it'll be fine. That said, what is the difference between quenching in water versus oil? Well, let's test it. When we test these with the files, both were harder than the 65 Rockwell file, so had maxed out the scale, and there was really no appreciable difference. That said, when you're not making steel yourself and are buying a nice commercial alloy, they'll often tell you what liquid to quench it in and precisely what temperature everything should be, as they'll have calibrated it to figure out which is best for that alloy. But in a pinch, either works. The knife picked up a slight bend to it after the quench, and in the freshly quenched state, it's actually too hard and risks being brittle. So what we're going to do is something called a shim temper. This means cooking the knife while it's clamped in a jig that is gently bending it straight. By cooking at about 450 degrees Celsius for an hour or two, the metal will soften a little bit, but become much more tough in exchange. The result is a balance between strength and hardness, so the final tool is ready for plenty of use and abuse. Or, at least, it should be. Turns out we really ought to have cooked that initial piece longer, because the blade came out dead soft after tempering, which is not ideal. So guess it's time for more case hardening. This time I had to weld up a quick and dirty box to fit the knife, and we cooked it for an hour to make sure that there was plenty of carbon deep into the blade. And when that was done, it has to get heated again, re-quenched, and re-tempered before I could finally do the finishing steps. But while I put a nice edge on this and a handle, why does any of this actually work? What's happening to the steel as it goes from soft to hard? It all comes down to crystal structure. Ironically, your weird aunt that goes on about the power of crystals is kind of right, just not in any of the ways that she means. While they can't balance our chakras or heal you through the magic of a jade crotch egg, understanding crystals and crystal structure is actually key to understanding quite a lot of our universe. Even though they may not seem crystalline when you see them in bulk, metals most definitely have a crystal structure and are made of many tiny crystal grains stuck together. Usually you can only see the grains with a microscope and a special surface treatment, but one exception is the beautiful banding that you see on slices of iron meteorite. The slower you cool a piece of metal, the bigger the crystals can grow, and since these bits of metal took literally millions of years to cool down from liquid to solid, the crystals grew to be gigantic. To help explain why crystal structure and alloying makes things stronger, we're going to reduce this to 2 dimensions to make it easier to understand. I first saw a version of this demo on Steve Mold's excellent channel, and I thought it would be perfect to help quickly explain this. I've got 2 sizes of steel balls here, and I've scaled them to be approximately the size of either iron or carbon atoms, respectively. Starting with just the red beads representing pure iron, you can see that the balls settle into distinct grains where chunks of the balls line up and stack neatly. But the chunks are separated by these defects that form a border around the grains. Each grain has a specific direction it's aligned in, and the atoms are most able to move in that direction. But because of neighboring grains are pointing in different directions, it limits the amounts that the atoms can move. Alright, now let's try an alloy. If we mix in a percentage of carbon atoms, or smaller BBs, we see that the grain structure is very different, and the small atoms induce a lot of new defects by fitting in and amongst the iron atoms. This makes the material much more grainy, meaning the crystals will have an even harder time finding a direction they can move in. This is not a perfect analogy, but it's enough that you hopefully get the idea. In the real world, this is complicated by the fact that atoms, unlike BBs, are electrostatically attracted to each other, and the chemical state of the atoms plays a huge role as well. Oh, and that third dimension is a bitch that adds a ton of complexity. But the important part is that by adding an alloying element, you can radically change the crystal structure that forms. Now when you heat and cool the metal, it will go through radically different crystal phases. When we heat and then quench steel, we're encouraging the metal to form a specific hard crystal structure called martensite. Then, by cooling it quickly, we lock in that structure before it can relax, leaving a hard material behind. By tempering the metal, we allow some of that crystal to relax into a softer form, giving us a balance of properties. If you'd like to learn more and really get into the weeds of ferrite versus cementite and body-centered cubic versus face-centered cubic and all that crystally goodness, Real Engineering and Alex Steele collaborated a few years ago to make an excellent deep dive into the science of this. However, something that rarely gets talked about on YouTube is that there's actually another element that we can put into iron to make it hard: nitrogen. Some steels, like most stainless steel we encounter, can't be hardened. Even if you try and put carbon into it, it just becomes a brittle mess because of the other elements that have been mixed into the iron. Or maybe you already have a great hard steel, but it's going to be used for something like a bearing surface, so you want it even harder to deal with the wear and tear. For both cases, you need to use nitrogen instead of carbon, or both at the same time. Now, nitrogen makes up 75% of the atmosphere, so you'd think that just cooking in air would work, but no. Molecular nitrogen is incredibly inert in most cases, so you need to either make it more reactive somehow, or use a more reactive nitrogen-containing molecule. The two ways to do this are plasma and salt. We actually attempted both, but only the latter worked. With plasma, the idea is you stick your bit of steel in a vacuum chamber filled with a tiny amount of nitrogen gas. Then you add high voltage to induce plasma to form. This ionizes the nitrogen, thus making it reactive, and by biasing the voltage, you can make it accelerate to incredibly high speed and slam into the metal. When this happens, some of the atoms literally embed themselves in the metal and then react with whatever's there. We tried this many times before realizing that our vacuum system is actually too good. We built it for doing plasma-based metal coating, and for that you want an incredibly deep vacuum. But for plasma nitriding, apparently you need much higher pressure. With vacuum chambers like this, you can gauge the pressure just by looking at it. If the plasma fills the entire chamber, the pressure is very low. But if the plasma is denser and hugs the metal, the pressure must be higher. This is because the higher the pressure, the less distance that electrons and ions can travel before smacking into something. In images of plasma nitriding that you can find online, you can see that plasma really hugs the metal. But the problem is that running at high pressure means more current and, importantly, a lot more heat buildup, something our system was never designed to handle. So if we want to nitride some steel, we need another method. And as I mentioned earlier, that means salt. Specifically molten salts. In this case, a 75 to 25% mix of potassium nitrate and potassium chloride. Industrially, they often use cyanide salts for this, as cyanide is a perfect mixture of both carbon and nitrogen, so you end up basically case hardening with both carbon and nitrogen at the same time. Of course, there's a tiny issue with this, in that molten cyanide is so unbelievably dangerous I lack the words to describe how hard I noped out of that idea. This is why we're using non-toxic potassium nitrate for this. However, even non-toxic, molten potassium nitrate is still a very strong oxidizer, and will break down and release bits of nitrogen oxides. So this still needs to be done in a very well-ventilated area. The potassium chloride we add to the mix acts as an antioxidant to help keep the surface of the metal nicer and not get rusted to hell from the intense oxidizing environment. Speaking of intense oxidation, one thing we realized as we were preparing for this experiment is that our normal graphite crucible probably would have turned into a bomb, or at least a very big fire if we'd tried this in it. Black powder is, after all, a nitrate salt and a carbon source, so a molten bath of nitrate probably would not do nice things to graphite. To remedy this, we picked up a nice alumina crucible which won't react. The bath needs to get up to about 650 degrees, which is much colder than the usual case hardening temperature. The metal parts to be treated can be dropped in, covered in the salt mix, and cooked for about 3 hours, though it does take time to add in all the salt as it reduces in size as it liquefies. This is much slower than normal case hardening, but it's also at a lower temperature. Though it also doesn't require a quench. The metal-nitrogen mix just becomes really hard on its own. The cool thing about this is that it even works on cheap stainless steel, so I can take an otherwise blunt butter knife, sharpen it, and then dunk it in the salt bath to make it into a hard cutting implement. Though the surface comes out looking pretty rough, so a very light polish is probably in order. The nitrogen-rich layer is not very deep though, so you don't want to polish it right off. Speaking of surface finish, you can see why the plasma treatment might be preferred, or at the very least using the cyanide salts, which would mar the surface less. The surface straight out of the salt isn't the prettiest. With plasma nitrided parts, the surface comes out glossy and nice, and at the end of the process you can change out the reactive gas for oxygen to blacken the surface and build a tough oxide to help prevent further rusting. But with that, we've covered all the DIY ways to turn iron into usable steel. Of course, modern industrial steelmaking is an art in and of itself that we haven't even touched on. The industry around its production uses some of the largest and hottest machines on Earth to produce billions of tons of the stuff every year. And when you have the ability to liquefy iron, controlling what elements you alloy and the precise carbon percentage becomes easy, making cementation a mostly lost process of the past. I only even heard about it because I got playing a Minecraft spin-off called Vintage Story, and after having to prospect for iron, run a bloomery, and tend a cementation furnace for a week just to create a small, precious amount of blistered steel, I knew I just had to give the process a try in real life. And I am so pleased that I did, because now I have a lovely new chef knife and a bunch of new skills and techniques I can use for future machining and forging projects. And I hope that this demonstrates that we don't need to obsess over the perfect alloy just to make a nice tool. There are lots of ways to take readily available, cheap materials and turn them into something that can be used and reused for many years to come. We've spent this video talking about ways to improve iron and make it stronger, and one of the main reasons that humans learned to master steel was the need for protection. Be it knights on the battlefield in their suits of armor, or the musket of a traveling merchant terrified by highwaymen. But these days, we spend far more of our time sitting behind a screen, and the ne'er-do-wells that want to do us harm don't even need to leave the comfort of their mother's basement. Every time you use the internet, you leave a trail of data behind that data brokers hoover up and sell to the lowest bidder. This leaves you vulnerable to scams, identity theft, spam, and all kinds of nefarious schemes. And while you do have a right to ask the data brokers to delete your data, tracking it all down manually and sending those requests is at best a Sisyphean task to do by hand. Thankfully, the sponsor of this video, Incogni, can be the shield that you need. Their system automatically hunts down the data brokers and gets your data removed. And with their new custom removal tool, if you find your data somewhere on the internet and you want it gone, you can point Incogni at it and off they go to get it taken down. Especially with the rise of AI hacking tools, data breaches at big companies seem to be happening more and more, leaving your data exposed. So if you want to start protecting your privacy today, head over to incogni.com/thoughtemporium or use the coupon code ThoughtEmporium to get 60% off the yearly plan. So don't wait. Snag this amazing offer while you can at incogni.com/thoughtemporium or use the code ThoughtEmporium at checkout to get 60% off your order.